Okay. Will be shipped with Tizen in the future. So we have this concept of smart home. So basically, there is another concept recently coming called the IoT, Internet of Things. So basically, everything you got, every electronic device you got will be connected to internet. So in order to facilitate that, we have this new operating system to the market called Tizen. And why Tizen? So you might be thinking like, okay, we have Android, we have iOS, we have a lot other mobile OS and similar. I mean, if even Android is having something similar to that of IoT. So why do we have Tizen? So these were the reason I was able to find out like why these people introduce or push up with the new OS. So one thing was like Micromax beats Samsung in India regarding the number of sales. So Samsung is like their plastic cell phones are losing the market a lot. And then basically they have to come up with. So these guys, Samsung and along with some other big gains like Intel and other 36 companies, they come up with Tizen, which should be a competitor to Android. Again, they actually place at a different level. They are not just looking into the mobile market. They are looking to everything, like right from what I told, like your TVs, washing machine, fridge, everything. So these are some of the gains that support the Tizen thing. So these are that consortium where they have like huge hardware vendors like Intel, Huawei, KT and all, and then again like the OEM developers like LG, Samsung, again the carriers like Docomo, Orange, Vodafone, etc. So a lot of guys are actually involved, and this is actually constantly changing. Some people find it difficult to deal with them; they'll drop. Some people will join them. So it's like a changing stuff. And I'm just quickly going to a Tizen application. So like your Android application, there are three types of application for Tizen also. It can be a native application, which is actually entirely written in C++. Again, you have this web application, which basically it's same thing like your Android only, but additional there is something called the Tizen web API. So the advantage is that Tizen actually provides a set of JavaScript function which allows you to interact with your device functionality like what your Wi-Fi, NFC, Bluetooth, whatnot. So in Android, it's a different way to do that. I'll come to that. Also, I'll talk about the security issue there. And again, you have a combination of both. That is a hybrid application which contain both web as well as native application. And this is basically the Tizen architecture. So in Android, your installation binaries will be .apk, right? In Tizen, it will be .tpk if it's written in C++. If it's a web app, it's a widget .wgt. And there will be in order to run these two particular application, there will be for Tizen TPK, they have Tizen native framework, and for widget they have Tizen web framework, which actually comprises of all those HTML5 plus Tizen web API. And all these components can directly interact with your device features like your multimedia, location, message, web, Bluetooth, whatnot. And again, it will at the lower level there will be the kernel. So it's always a higher abstraction to the top and the lower one at the bottom. So this is the Tizen web API. So I told like Tizen is having a separate set of APIs called the web APIs. So basically they are used to interact with all your device functionalities. Now basically JavaScript got the power. I mean these days you can see like JavaScript is used in not server, server side thing and a lot of things. So JavaScript is basically getting a lot of power. So this set of these are basically JavaScript APIs exposed in Tizen, which allows you to directly interact with a lot of features in the device. And let's have a look into the Tizen application structure. We have native apps, web apps, and hybrid apps. And basically, Tizen is a Linux OS, Linux-based OS. It's a very lightweight OS. So, like in generic comparison with Android, the advantage of Tizen is it doesn't look that great, but it's very lightweight because it's written in C++. That's one reason, and it requires very less hardware. It performs as much as what Android gives, plus it got some additional features which Android is lacking. And this is how the apps got installed. So in your Android, you have something like com.something.something or org.something.something when it got installed, right? If you are familiar with Android application, the installation structure. So here in Tizen, it will be installed under /ops/user/apps. And every app will be having a random ID which comprises of alphanumeric characters and numbers like this. So this is a typical developer-developed application that is like something inbuilt with Tizen. So these are the application which get installed. So this is the directory where application get installed. Now this is the structure of a TPK. So if you extract a TPK, basically what you can find is the content that is over that side, that's on the blue. It can have the different executables. Like the executables are ending with something .exe. It's not a Windows exe, but still they are using that convention. And there is a executable. Then you have the manifest file. This manifest file is basically like your Android manifest.xml. Again, there's a couple of other directories also. So when you install a TPK, every content will get extracted to /op/users/apps and that alphanumeric package ID, and then inside that folder this content will get extracted. So this is how the installation happens, very simple. Again, similar for web app. So web app, it's like these are the contents that in red is the contents of web app, and basically your HTML, JavaScript, CSS, and config.xml, similar to your manifest.xml in Android manifest.xml, and it will get extracted to the same thing like /op/user and so on. And again, the hybrid application. So hybrid application is basically a combination of both. It can have the binaries as well as the HTML5 based thing. Now let's start with the security of Tizen. The security model of Tizen, like any other application like mobile OS or other operating system, it's having like every application runs under the same UID called app, and then it's not, yeah. So basically most of the daemons will run under non-root user, but right now there's a lot of things running under root, so there is an issue if a lot of processes are running in root, which I'm not going to cover today, but most of them are not running under root user. Again, it's having like application sandbox. So in Android there is a sandbox. So in Tizen the sandbox is called SMAC. That's something called the symbol mandatory access control. So basically they call it like SMAC and they made it too complex, but it's just have an understanding that it's just a sandbox. So what it does is like it doesn't allow application A to interact with the files and contents of application B and vice versa. So there is a sandbox, there's a container kind of environment. So that's what it does. And then the permission model, there's a least permission model. Like your Android, in Tizen they have something called manifest.xml as well as config.xml. So basically these are the files that specify the permission and like SMAC rules and all those related stuff. Again, in Tizen, the advantage is for web application, it directly and it's mandated to impose CSP. CSP is nothing but the content security policy, which are a bust in web application security these days. So it's mandatory with Tizen. Again, I told you like you can use web API, right? So you can directly write application which are so powerful with having complex logic and all those stuff. So you might want to, you don't want anyone to get your source code, right? So it actually allows you to encrypt all these contents, and it's actually encrypts at install time and will get decrypted at runtime. That's a model. And again, there is something called, so basically McAfee is an Intel company. So McAfee had incorporated something called the content security framework. So what it does is like you have a lot of antivirus software, right? So this actually is a set of APIs which provide access to the low level component of the OS so that your antivirus can easily coexist with the system. It allows you to scan all the data, all the URLs that is being passed, all the dynamic things that is happening. It allows you to do that. So that's why they have the content security framework. And this is a SMAC model, basically nothing but the sandbox. So web app 1 won't be able to access the contents of web app 2 in the file system. So there's a lot of things here, but this is the basic idea. Like it's a sandbox. So the basic simple idea you should know is like whatever mine is mine and whatever yours is yours. I don't have any hand in whatever you got and you don't have the thing in vice versa. So that is the basic sandbox rule. So SMAC actually allows us to extend this rule. So like if I want to do an IPC with that guy, I should specify some permission and set of consent things like that. So they have such things. And again, like WebKit 2. So this is one thing that, so you know that Tizen is Tizen support web application. So this basically runs on top of WebKit 2. So it's actually an API layer implemented over WebKit. And you know that there is a lot of vulnerabilities on WebKit these days. Like you have seen a lot of use after fees, like a lot of stuff. So basically it supports something called a split process model. If you use Google Chrome, you can see that you have different tabs, right? So these tabs are running as a different process. If you check in your process manager, you can see that each of these tabs are actually running as a separate process. So if something happened to one tab, it should not affect the others. So that's why we have, in Tizen they have this particular security model. Like they are using WebKit 2. So if something happens, so some attacker got access to some, some web app 1, it should not affect the contents or whatever things related with web app 2. So that is the basic idea, but still there are a lot of things. Again, so finally, I'm just stopping with my theory here. So it's a quick comparison. We have Android where the apps is identified by UID, and in Tizen it's identified by UID called app. Again, in iOS, all the apps run under the user mobile. Android is having a permission model, which is based on Android manifest.xml. Again, Tizen is also having the same permission model, which is based on sorry, manifest.xml and config.xml. So basically, config.xml is for web apps, and manifest.xml is for native applications. And then the IPC is based on binder using indents in Android. Again, you have a message port IPC using sockets, and in iOS you have a lot of workaround like match port, distributed notification, XPC based on IPC, and a lot of other stuff. And the sandbox is combined with SC Linux in Android. Again, here in Tizen it's a SMAC plus CSP, and it's the application, the signing model in Android is it's actually signed by the developer. Again, in Tizen it should be signed by the developer as well as a distributor. That's a store owner. Like if you have Play Store or Tizen Store, they should actually sign it. So that is a security model in Tizen. And here the sandbox can be Powerbox or Seatbelt, and it's actually signed by the distributor. Here in iOS there is no permission model as such. So basically, like whenever you run an app, if it needs a permission, it will ask you like, do you want to allow this? So that's how the permission model with iOS. And enough. Let's act Tizen. Okay. So my research focus was basically on Tizen web apps, the Tizen OS memory protection mechanism, and around the Tizen CSP and WebKit. So it's actually an ongoing research. And I would like to give a quick comparison on Android web apps to Tizen web apps. So, like, how many of you are Android developers here? You're Android developer, right? Come on, like, how you will leverage the device functionality using? Okay, you're a POC guy. Cool. So, if you are an Android developer, you might know that you need something called the add JavaScript interface. So basically, it's a bridge that allows your HTML web application to communicate directly to your device functionalities. So basically, the advantage of Tizen is that you have to implement a lot of stuff. Like if I want to use, if my web app want to use Bluetooth in Android, I have to say that I have to define a bridge telling that my Bluetooth API is exposed to this particular label, and you can call this particular JavaScript function to use it. I have to write that code. In Tizen, you don't have to do that because they have a lot of web APIs. Just directly call the web API, it will do the function. Again, that's actually protected by your permission model and stuff like that. Okay, so I'll talk about a real-time scenario. So consider this an Android application and that's a Tizen application. So you have your device which is having Bluetooth, NFC functionality. So in order to access Bluetooth or NFC, you need to have the permission, Bluetooth permission and NFC permission. So in this application, actually I'm using only Bluetooth. So some developer unknowingly he gave the NFC permission. So basically that's an overprivileged permission. So like I am not using it, but still I'm giving that permission there. So in order to access Bluetooth in Android, I have to expose some API to the bridge, the JavaScript bridge, so that the bridge can access it. So I expose my Bluetooth. I did not my NFC, but still it's overprivileged. So that's the model here. Again, in Tizen web app, the similar thing. It's here the permission is called privilege. So I have Bluetooth permission privilege and NFC privilege, and this NFC privilege is overprivileged. I'm not using it, but still I'm just using that privilege. But the thing is that I'm not using it, and there is Bluetooth API and NFC API, which is a part of the Tizen web API, and it's already implemented. You don't have to implement, and you have the functionalities, Bluetooth and device. Now, consider the scenario when you have an XSS. So if your web app is having an XSS, what can go wrong in Android is that the XSS can actually make a call of that, find out that particular JavaScript call in the bridge and make a call to Bluetooth permission and directly access your Bluetooth. But again, if there is an XSS, still even if you have NFC permission, it doesn't allow you to access NFC. Why? Because this developer does not expose us. He did not write the code to expose that particular API to the bridge. So that's an issue there. So that's not an issue, that's a secure thing over there. But see what happens in Tizen. We have all the APIs already with the Tizen web API. So if an XSS happens and if NFC privilege is there, definitely it can directly call the NFC API and access NFC. So the threat space or attack space is more considered to Android. But again, they have something called the CSP along with it. So basically CSP will restrict a lot of stuff in real world. But talking about a scenario. Okay, so now I'm going to show about the things which I had discovered in Tizen. Like it's based on, so basically shell shock was there. So it was there, it was reported, and I think it was fixed in this device. This device is running Tizen 2.3. My research is all concentrated on Tizen 2.2. And how many of you know about the concept of DEP? Some people might be knowing, right? So basically what data execution prevention does is like, if some attacker is able to get in control of your application and he is able to inject some malicious code, which we commonly call as something called shell code, if it actually gets into the stack. So if DEP is enabled, that means stack is not executable. So whatever you inject in the stack, it won't get executed. If it is not there, like that shellcode or whatever get executed, and attacker can do whatever he want. So basically, dep should be a part of every operating system. It's a basic, like the least basic thing that should be a part of every operating system. And basically, the dep was not shown in action. I'll show you a demo of that. This is basically a shell code, which is nothing but your exit shell code, like move 1 to AL. If you are not familiar with assembly, like move 1 to AL, store out EBX, and then call the interrupt for exit shell code. So basically, this nothing but exit 0 in your C program. So what I try to do is I try to copy this particular code into the stack and then try to execute it. So if dep was there, this should not execute. Okay. So basically, this is a Tizen IDE. Like you have the Android IDE, like Android Studio or whatever. This is a Tizen IDE. So I have a Tizen emulator running over there, and I'm just running this application. And you can see that buffer. The name of the app is buffer. Buffer has been closed. That means our shellcode basically worked. It basically was an exit shellcode. It worked. So dep was not in scene. If dep was there, this shouldn't be allowed. Again, coming back to the presentation. Okay, so how many of you know about ASLR? Okay, if you guys know, it's good. So basically, ASLR is nothing but whenever you have an application, like you have a binary, when you run it, there is a base address and some other, it's actually mapped to a particular address in the memory. So like, for example, if I want to, if I'm an exploit writer, if I want to develop an exploit, so basically what I will do is like, if the address are constant, I can like find out like which function is called at where. So basically I can directly give that address and I can make my exploit work. So that is one thing related with exploit development. So ASLR is basically something called address space layout randomization. It's a protection technique which is used to counter this exploit development process. So in order to make it very difficult, so what it does is like every time you run an application, the memory address on which it is mapping to will be different. Like it will be rebased every time. So if ASLR was there, like it won't be. You will find it very difficult to write a reliable exploit. So ASLR, it's like in Android, it's like it was a serial hierarchy. It was partially supported in one version, again partially in some other version, and completely like in 5.0, it's fully supported. But with Tizen, it's fully supported. Right from the first version, it's fully supported. ASLR is fully supported. So as per the documentation, it's fully supported. And in Tizen 2.1, 2.2.1, it's actually discovered to be not existing, or like it's broken by some researcher called S. Suzuki, whatever. So basically, if you want to check whether ASLR is enabled in a system, Linux-based system, you can just go to /proc/sys/kernel/randomize_va_space, and if it is set to 2, that means ASLR is enabled. So in Tizen 2.1, the issue was there is something other called /proc/self/personality. So if it was set to 0040000, then that means sorry, that means address no randomized. So basically, you are enabling ASLR at one place and you are disabling at some other place. So that was the issue with the previous version. The developers messed up or whatever, I don't know. So again, they passed the issue in Tizen 2.2, which is my scope of research. So again, they said something personality value, something called a bunch of zeros, which I actually checked the doc and I was not able to. I checked the personality.h header file. I was not able to find like what exactly that corresponds to. Okay, so let's see. Let's try that. How that work? I tried it. So again, if you see the compiler instruction, it's having a flag called -f PIE. So basically, PIE means position independent executable. That means you have to compile that executable with ASLR enabled. So if you compile it with this flag, that means your executable is compiled with ASLR enabled. But let's see what happened. I'll just quickly go to the demo. How much time? How much more time I have? 10 more minutes. Okay, cool. So again, this is an application. That's my emulator running over there. It's nothing but it's having a box like OK box. When you click on OK, like it will exit 0. It will just exit out of the application. So that is the functionality of this app. So that is the app. Hello Tizen. You click on OK, it will just close out. So this is the app, and so if you just go to your compiler instruction, like in properties, if you go to C++ build, and you can see that that flag is there. So that means the exe, like the executable is, it's visible, right? FPI. So basically that means the variable is compiled with it's ASLR enabled during the compilation. So what I'm going to do is I'm just directly accessing the shell. So here I'm just showing you that randomize underscore VA. So this basically tell me that it's set to 2, that means ASLR is enabled. And again, I'm just going to this personality value where the previous issue was there. So now they actually set it to something called something like 000, which is actually not documented anywhere. I mean, I was not able to find what it actually corresponds to. Okay, so what I'm going to do is, now I'll show like how the memory mapping is there. So if the memory mapping is the same when you run your app 2 times, that means ASLR is not there. If ASLR is there, then every time you run your application, the memory map address should be rebased actually. So I'm running the app there, and I'm just finding out it from the process list. So basically my app, like I told you, like every app will be having a random alphanumeric package ID. So here I'm finding out my package ID. So my package ID is something like APSCI CX2B E7, something like that. So like just like your com dot something in Android. So I'm running that particular thing, and here it's actually running under app UID, which I mean as I mentioned before, and I'm just looking out the memory map of that particular process. So /proc/maps, sorry, the PID slash maps will give me the process ID. So basically APSI corresponds to the PID 4305. So I'm just giving that PID and then maps. So you can see that this is how the memory map looks like. And on that side, if you see, you can see that see there is an exe ASLR.exe. So that is a binary, and it's loaded at some address over here. Let's do one again. Close it. Again, we are opening it one more time. And let's do the same thing once again. Let's see where the memory address is. So again, I'm just trying to find out the PID of the new process. So again, it corresponds to the PID 4315 under the app user. So again, I try to print out the map. So this time if ASLR was enabled, it should actually load under a different memory address. Like it should be rebased. So now you see something like, if you check over here, it actually, the binary actually start from B71 3D000. Okay. And if you check over there, like I will mark it for a little bit clarity. So see the starting address there, B71D000, and see the starting address over here. It's exactly the same. So that means ASLR is not in the role, not in the scene. So that is how, that's the issue with the ASLR over there. Again, moving back to the demo. Yeah, so one more vulnerability I was able to identify, that was URL address spoofing or content injection. So basically what it does is, like, you open a new tab, like with your JavaScript, let's call it be facebook.com, and you can actually arbitrarily write content to it. So that is something cool. Your URL will be facebook.com and the content will be whatever you control. Let's have a demo of that. So this is one interesting vulnerability. So this is a POC page under opensecurity.in. So this is a place where I like publish all the research, all my findings, everything, all my tools, everything. There is a page called like in the previous page. Like if you open that one, it will actually open a new tab. So basically, this is the expected behavior. When you open it, it should be open a new tab and tell that about.blank. It should not have any URL assigned with it. So this is a basic JavaScript. Open facebook.com and try to write something into it. So the correct behavior is that open it in a new tab and write the content, but the URL should not be facebook.com because you are not writing into facebook.com. So this is the expected behavior. So Chrome is showing the expected behavior. The same thing I'm actually running in the Tizen browser. Let's see what happens. Okay, so here I have the Tizen WebKit based browser. It's a by default shipped with Tizen. So I'm just running opensecurity.in slash lab slash Tizen slash Tizen.html. So what happens is that at the bottom you can see it's showing facebook.com and the content is you have been hacked. So basically you can control a particular arbitrary window. So the URL is still facebook.com and the content is something. I'm just showing you have been hacked. I can write almost anything. I can write a phishing page or whatever. So see that it's a new tab open, but the URL still points to facebook.com. So this is one vulnerability existing in Tizen. It was existing. It's fixed now. I reported it and it's fixed now. So that is about that. Now we have content security policy. So how many of you know about CSP, content security policy? Most of the web security pentesters should be knowing about it. Anyway, so basically it's kind of whitelist which basically tells from where should from where my site should load content, like from where my site should load script, from where my site should load iframe, from where it should allow, and a lot of other stuff. So basically it's a set of whitelist. So this content security policy which tells that default SRC self, like by default load everything from same domain, don't load it from anywhere else. It's actually a header, okay? It's a response header. If you are not aware, it's a response header. Again, it tells that script SRC cell only load JavaScript files from the same domain. Don't load it from anywhere else. So that's what it tells. So this is actually a bypass for that. I'll directly go into the demo and I'll explain over there. So again, I have a POC page at opensecurity.in. So it's a CSP bypass. So what happens is that if you see the source code, it's nothing but I'm creating a script tag. So basically once I click that particular button, it will call the bypass function. Inside that bypass function, I define like document.createElement, create a script tag, put the ID to that X and give the XRC/U00. So this is a JavaScript null byte which basically bypasses the CSP and load a script file from GitHub, rawgit.something. So basically if CSP is there, it should not allow to load whatever malfication I did with the URL. So basically it's nothing but script ID is X and SRC is equal to that one and then closing the script tag. That's what I'm dynamically doing. So if I go to that particular script file, the content of that will be like hey, I'm from GitHub. So if CSP is there, which basically tells that load everything from my domain and also load script only from my domain. So that means it should not allow you to load from this one. So if you go to your console and if you just hit it, you can see the response header there. Okay, so you can see that content security policy default SRC self, colon script SRC self. So basically the CSP is defined over there and come on. Okay. So CSP is defined over there and I'm coming back, I'm going to my console and then I'm trying to hit that button. So since Chrome CSP, this was actually found in WebKit and they actually fixed it. That's why it's telling refuse to execute inline script because it's a violation of CSP. So basically your Chrome does not allow you to execute it. Let's try to open the same thing in your Tizen browser and let's see what happens. Okay, so here I have the Tizen browser. I'm just visiting the same page. So there's the same button. And if CSP is there, when I click, the script should not execute from GitHub. But there you go. So basically, that basically bypass your CSP, content security policy. So that's all I got for the demo today. And I have a couple of things which actually, I don't have time to cover it. But still, I'll just conclude it. Like the security model or architecture wise, they have put a lot of effort compared to Android. Like they have a lot of checks in place. But when you make things complex, the chance of getting messed up is huge. So they have something called, I told about SMAC, right? So basically SMAC is having some rules, like 41,000 SMAC rules are there. So it's high chance that developer will get messed up. So that is one thing. Anyway, it looks promising. They have fixed all those things which I had shown here in the latest build, which is available in the device. Where is my device? Okay, cool. Okay, it's in safe hand. So that's all pretty much about Tizen. Thank you. Yeah. Pardon? Yeah, it will work. So there is something called Tizen IVE. So basically, that is for your cars or something like that. If you want to have infotainment, entertainment system or something like that. So that's for a car. Same thing you can run on your Raspberry Pi, your desktop or whatsoever. It's just a Linux one, which basically is having a lot of security restrictions and all those things by design. Pardon? This is actually x86. I think it support ARM also because that processor should be ARM. Yeah. Any? Yeah. That bypass was the null byte /u. So basically, null byte. So basically, if you see the URL, like for the normal legitimate CSP parser to parse the rule, it should see that that should be like it somehow tricked the particular parser and executed that. So basically, that acts as a JavaScript escape byte, which basically might be some implementation mistake in the CSP parser they have. Yeah. Any other questions? Yeah. Huh. Yeah. So with Tizen, by default, they have something called the like the network, some dynamic analysis framework. But I don't think from a security perspective it will be too much. Basically, I'm working on something, and I'll be presenting the same at probably at HITB Amsterdam soon. So I'm working on something. So once that is done, I'll publish it. It will be open source probably. So that's it. That's all. Thanks.